We've used cylindrical tableau to compute power sum trace evaluations, and there's other tableau that we can use as well, which are called cyclically row-semistrict. So given a poset P, call a tableau cyclically row-semistrict. If it's row-semistrict, and if in each row we have that the rightmost element is not greater than the first element. So it's descent free, including last element to the first. Can't be a descent either. So for example, let's say P is the poset on these four elements. It looks kind of like an N, and let's let lambda be 3, 1, and we'll draw cyclically row-semistrict P tableau of shape 3, 1. So we've got one element all by itself. Let's say 4 is all by itself. And then we have to arrange the other three elements so that the first is not greater than the second, which is not greater than the third, which is not greater than the first. So if we write 1, 2, 3, that won't work because 3 is greater in the poset than 1. We could have 1, 3, 2. 1 is not greater than 3, 3 is not greater than 2, 2 is not greater than 1. So that works. And then once we've got this cycle going here, I guess we could start it at any position. And we've got 3 different cyclically row-semistrict tableau of shape 3, 1 with 4 on top. Now if we put 3 on top, then the other elements are 1, 2, and 4. That's no good because 4 is greater than 1. Unfortunately, 4 is greater than 2 also. So no matter where 4 is in this cycle, it's going to be greater than what comes after it. So I think having 3 in the second row is just not a possibility. If we have 2 in the second row, then the other elements are 1, 3, 4. And here 4 is greater than 1, so that also doesn't work. Unfortunately, 3 is greater than 1. So whatever comes before 1 cyclically is going to cause a descent. So we can't have any cyclically row-semistrict tableau that have just 2 in the second row. Now if we put 1 there, 2, 3, 4, that doesn't work because 4 is greater than 2. But we can write 2, 4, 3, and then 3 is not greater than 2, so that works. And then once we have that, I guess we can cyclically rotate the last 3, the 3 elements in the first row, and get 4, 3, 2, or 3, 2, 4. So it looks like there's 6 cyclically row-semistrict tableau of shape 3, 1 for this poset. It turns out that if we, say, fix a partition of n, and then let's let W and Sn avoid the patterns 3, 4, 1, 2 and 4, 2, 3, 1. then if we apply the power sum trace psi lambda at the Kaj-down-listic basis element of Sn indexed by W, this equals, we have three interpretations here. So the number of cyclically row semi-strict P of FW tableau of shape lambda also it equals lambda 1 times all the parts multiplied from lambda 1 to lambda r times the number of left anchored, so that means the lowest index comes first, cyclically row semi-strict PF tableau of shape lambda. And also, maybe I won't write this separately, it equals lambda 1 through lambda r multiplied times the number of right anchored, because we could just pick that lowest element to go either all the way on the left or all the way on the right. So in this example, let's let W be 2, 3, 4, 1, so that FW equals that planar network, so that the pose set equals this pose set that we just did. Then in that case, let me erase these bad tableaux to make more space. We have psi 3, 1 of the Kaj-down-listic basis element CW equal to 6 for the 1, 2, 3, 4, 5, 6 tableau. We could also say it equals 3 times 1 times the number of left anchored cyclically row semi-strict tableau. So that means lowest index on the left, lowest index on the left. So 3 times 1 times 2 is 6. And then we could also use right anchored. So lowest index on the right, lowest index on the right, 3 times 1 times 2 equals 6. All right, now we can prove the validity of this proposition by stating a bijection between cylindrical tableau and row semi-strict, cyclically row semi-strict tableau. Now statements 2 and 3 follow pretty easily from 1, because well, that's basically how we did 1. We found one that was left anchored and then rotated that last row as many times as we could, which was lambda 1 times. We could put that lowest entry on the right and then rotate it lambda 1 times. So the statements 2 and 3 follow immediately from statement 1. So let's just prove number 1. So now we're starting with W, avoiding these patterns. Let's let V be the unique 3, 1, 2 avoiding permutation satisfying the pose set of FV is isomorphic to the pose set of FW. And let's let row 1 through row n be the unique path family of type E covering FW. Alright, so let's start with a cylindrical tableau. Let U be a cylindrical tableau. Of shape lambda, and let's let its kth row contain, we'll say I1, I2, I2, I3. Since this is cylindrical, every path needs to start where the previous one ended. Let's see, this row is the kth row, so it has lambda k boxes. And then the first path has to start where that last path ended. Alright, now let's use these indices. And then we'll create a, well, actually this is not a PFW tableau because that would mean it had to have a path family of type identity, and it doesn't. But it is an FW tableau because it has some path family in it. So now let's create a PFV tableau. So that is a tableau using the unique path family of type E. We'll do that by taking the kth row to be, we'll take the first indices I1, I2 up to I lambda k in reverse order. So row I lambda k, row I lambda k minus 1, row 2, row 1. So we'll take those paths out of the unique path family of type identity and make them the kth row. You know, since there exists a path in FV, from source I lambda k to sink I1, then we can't have I1 greater than I lambda k in the path close at PFV. Because if there's a path to get from I lambda k to I1, that means that the path from I lambda k to I lambda k is going to have to touch the path from I1 to I1. So this is not great. This is not greater than I lambda k, and then I lambda k, the path rho I lambda k is not greater than the path rho I lambda k minus 1. Maybe I'll just use the indices. I lambda k is not greater than I lambda k minus 1, etc. So we do get a tableau that's cyclically row semi-strict. And we didn't quite show this is a bijection, but it's not too hard to show that this is a bijection. Now let's talk about Q analogs. So we want to write something like the power sum trace evaluated at the Cauchy-Johnson basis element of the Hecke algebra equals a sum over appropriate tableau Q to some statistic applied to that tableau. So appropriate tableau would be the three types of tableau that came from the result before. So no result is known for cyclically row semi-strict tableau or left anchored cyclically row semi-strict tableau. But there is a result for right anchored cyclically row semi-strict tableau. So this result is due to Shureshi Wax and Athanasiadis. Well, something similar is due to them. They actually didn't know that they were applying power sum traces to Cauchy-Johnson basis elements. But from their result, we can get this. So here W is 3, 4, 1, 2, 4, 2, 3, 1 avoiding. This is Q analog of lambda 1 product up to Q analog of lambda r. The sum of, I'm not going to have enough space. The sum over U right anchored and cyclically row semi-strict Q to the number of inversions of, no, it's not quite row 1, row 2, row 3 of the tableau. It's row 1 written backwards, concatenated with row 2 written backwards, all the way to the last row. So let me put the tableau we found back up here. So the right anchored cyclically row semi-strict tableau we found were 4, 3, 2, 1. Well, the example is for W equal 2, 3, 4, 1. P of FW equal to this n poset. And then the right anchored cyclically row semi-strict tableau we found were 4, 3, 2, 1 and 1, 4, 3, 2. And these are P inversions. We're only counting inversions between elements of the poset that are incomparable. So we have to write the first row backwards and then the second row backwards. Well, the second row only has one element. So this becomes 2, 3, 4, 1. And then, well, there can't be any inversions here because the indices are all increasing, so we have Q to the 0th. And here we have potential inversions between 2 and 1, 3 of 1, and 4 and 1. 2 and 1 are incomparable, but 3 and 1 are not, 4 and 1 are not. So we only count the 2 to 1 inversion, so we get Q to the first. So chi 3, 1 Q of this chi-Stahlistic basis element equals 3Q times 1Q because of the 3, 1 times 1 plus Q. So that's 1 plus Q times Q analog of 3, 1 plus Q squared. So that is 1 plus 2Q plus 2Q squared plus Q cubed. Now I wonder a couple of things about this result. First of all, I wonder if we can replace the exponent by P inversions of just U1, U2 up to UR. Or maybe even backwards. So UR minus 1, U2, U1. So we don't have to reverse every single row. I don't know. Also, I wonder, can we modify this to apply to left anchored cyclically row-semistrict p-tableau. I suspect that this is possible and not too hard, but I haven't tried hard enough to do it. And I wonder if turning a planar network upside down is going to be one of the ingredients. So if V and W are two permutations such that the poset of FW, well, such that if FV equals FW upside down, so something like now this isn't a descending star network anymore, so maybe I should say P of this equals P of that upside down. So here we have this poset is 1 is incomparable to 2 and 3 but less than 4. And then 2 is less than 4 also, and 3 touches 4 and touches 1 and 2, so it's incomparable to everything. And then this poset would be like that. So it's sometimes called the dual of this poset. So if V and W are related so that the posets are the same except one is upside down, then for all traces of the Hecke algebra, we have that trace applied to CV equals that trace applied to CW. And the reason, I'll give you an idea why this is true, is that W and V are related by conjugating V by the longest element in the symmetric group. And it turns out that if we do a similar conjugation in the Hecke algebra, then we get the Kaj-Domlistic basis element CW. Now, conjugating by W naught has the effect of switching generators from, so the first generator goes to the last one, the second generator goes to the second to last one, which is like saying that the wiring diagram gets flipped upside down. And also I want to mention, so this might look like a slightly disturbing fact, so conjugation doesn't always work like this. So it's not always true that TU CV TU inverse equals C U V U inverse. So conjugation in the Hickey algebra does not correspond in general to conjugation in the symmetric group for the subscript here. It just happens to work that way when W naught is the longest element in the symmetric group. Now if anyone can extend the formula or transfer the formula from right-anchored cyclically row-semistrict tableau to left-anchored cyclically row-semistrict tableau, that would be great. It's probably, I said it was not too hard, but it's probably harder than a homework problem. It's more like a research problem. So if that's something you want to spend a little time on, let me know. The end.